It is genuinely, like, it's wild to think about what actually happens when you just tap your smartphone screen.
Oh, totally. We take it completely for granted.
Right. I mean, you're just sitting on your couch, you open an app, you tap a button to order food or check your bank balance or whatever, and within a fraction of a second, the screen updates.
Yeah, it feels like magic.
It really does. But underneath that simple piece of glass, that single tap, is triggering this incredibly complex, globally distributed chain reaction.
A massive reaction.
Yeah, it's firing invisible signals across the air, diving into underground fiber optic cables, hitting server farms halfway across the country, and coming all the way back to you.
And it does all that in milliseconds.
Exactly. And today for our deep dive, we actually have our hands on the exact schematics for that reaction.
We do. Because, we're so accustomed to the seamless experience on the front end, like the pretty buttons and the smooth animations.
Like the stuff you actually see.
Exactly.
Yeah.
So that massive logistical operation happening in the background just becomes completely invisible to the user.
But when we look at the source material we have today, which is this document called Laravel 12 API Blueprints, we are essentially peeling back the drywall of the internet.
That's a great way to put it.
Yeah, we're looking at the foundational plumbing and the electrical wiring that dictates how modern, highly scalable applications actually communicate with each other.
And it's fascinating because it takes something that seems like pure arcane wizardry and breaks it down into a very logical blueprint.
It really does. And I want to get straight into the mechanics of this, because the document uses this incredibly grounding analogy before it even touches a single line of code.
The restaurant analogy.
Yes, it maps this entire complex digital architecture to something we all understand intuitively, which is just going out to a restaurant.
Right, and the restaurant analogy is a total staple in software architecture.
Why is that?
Well, because the physical constraints of dining out mirror the digital constraints of the client-server model almost flawlessly.
Okay, break that down for me.
So when you go to a restaurant, you sitting at the table, you represent the client.
Okay, so in the digital realm, I'm the web browser, or like the mobile app on my phone.
Exactly. You are the entity that wants something. But you can't just stroll into the back kitchen, start rummaging through the refrigerators, and fire up the stove yourself.
I mean, they would call the police.
Right. Because you have no idea where the ingredients are stored, you haven't been trained on their specific safety protocols, and you don't even know the recipe.
Yeah, that makes sense. So that physical separation is the whole point.
It is. You need an intermediary. So you look at the menu and you place an order.
Which in the digital equivalent, that order is a request.
Bingo. But you don't just shout that request into the void, right? You give it to the waiter. The waiter is the API, the application programming interface.
So the waiter's entire job is to take my highly specific request and carry it through the swinging doors into the kitchen.
Exactly. And the kitchen represents our backend server and database.
Right, because the kitchen contains all the raw data, the ingredients, and the complex logic to prepare exactly what I asked for.
Right. And then once the meal is cooked and plated, the waiter brings the food, which is the response, back to your table.
Okay, so the API is purely a messenger. I mean, it doesn't cook the food, it doesn't eat the food.
Not at all.
It just facilitates the exact communication between the person who wants something and the isolated system that possesses it.
That is the core of it, yeah. But let's actually map those physical actions to the technical terminology outlined in the blueprint.
Let's do it.
So when the client side formulates that request, it isn't using spoken English, obviously.
Right, it's using standardized communication protocols.
Exactly. Most commonly HTTP or HTTPS. And it uses specific HTTP methods to declare its intent.
Like the verbs of the sentence.
Yes. So if you want to retrieve your bank balance, your app sends a GET request.
Okay,
If you are registering a brand new account, it sends a POST request.
makes sense.
If you're updating your profile picture, that might be a PUT or a PAT-CH request. And if you're deleting a comment, it sends a delete request.
Okay, I'm following.
And this request often carries a payload of data called a request body, and crucially, a cryptographic token to prove your identity.
Wait, let me stop you there on the token. Is that like the equivalent of the waiter asking to see my ID before bringing me a cocktail?
That is a perfect parallel, yeah. The waiter needs verifiable proof that you are legally allowed to order that specific item.
Right, because anyone could just sit down and ask for a drink.
Exactly. So once the API waiter verifies your token, it carries the request to the server side.
And the server isn't just one magic box, right?
No, not usually. It typically consists of a web server that listens for the network traffic, the actual database where information is permanently written to disk, and the application logic that connects the two.
Okay, so this server complex processes the request and hands back a response to the API.
Right, and this response isn't just the raw data, it includes a meta layer of information,
Like what?
like an HTTP status code in the header. So a 200 OK means everything went perfectly.
Or a 404, not found, meaning the kitchen is completely out of that item.
Exactly. And finally, you get the response body, which is the actual data you requested, formatted in a clean, universal language like JSON.
Okay, so the restaurant analogy is a great way to visualize the flow. But if the internet is just millions of different restaurants, how is it not pure chaos?
What do you mean?
Well, if every single developer creates their own version of a waiter with their own unique menus and completely different rules for how to order, I mean, how does any system ever talk to another system?
It would be a nightmare.
Right. There has to be some kind of universal health code or standardized operating procedure.
And there is. The internet avoids that chaos precisely because the vast majority of these digital restaurants adhere to a very strict set of architectural constraints.
Okay, what is this framework called?
It's known as REST, which stands for Representational State Transfer.
Okay, REST.
Yeah, and it was codified by a computer scientist named Roy Fielding in his doctoral dissertation back in the year 2000.
Oh, wow, so it's been around for a while.
It has, and he defined 6 specific principles of REST. If an API follows these 6 rules, it's considered RESTful.
And what the blueprint demonstrates so clearly is that understanding these 6 rules is basically the prerequisite for understanding the physics of modern web architecture.
Absolutely.
So let's put these rules under the microscope, because the source document explicitly maps out the theoretical constraint, what it actually means for the architecture, and the tangible benefit for the developers building the apps.
Right. So the first principle is client server.
We touched on this slightly with the restaurant, but from a strict architectural standpoint, this mandates an absolute separation of concerns between the user interface, the client, and the data storage mechanisms, the server.
Right. They must be completely distinct entities that operate independently of one another.
But, I mean, I understand they are separate, but why is that a hard, unbreakable rule?
Well, yeah.
Like, if I'm building a simple app, wouldn't it just be faster to bundle the interface and the database together into one single program?
I mean, yeah, it might be faster for a quick prototype, but it is an absolute death sentence for a growing business.
Really? Why?
Think about how software used to be built decades ago, back in the era of desktop CD-ROMs.
Oh, yeah, the massive installer disks.
Exactly. The interface, the logic, and the local data storage were all tightly compiled into one giant monolithic program.
Right.
So if the design team wanted to change the color of a specific button or fix a typo in a menu, the engineering team had to recompile and redistribute the entire massive application.
Oh, that sounds awful.
It was. But by enforcing a strict client-server separation, the front end and the back end are decoupled.
Okay, so my iOS team can completely redesign the iPhone app from the ground up, changing every single screen without the back-end database engineers needing to touch a single line of server code.
Exactly. As long as the API waiter in the middle still speaks the same agreed-upon language, the two sides can evolve at entirely different speeds.
Okay, so it prevents a bottleneck where front-end and back-end developers are constantly tripping over each other.
Yep. Which leads us to the second principle, cacheability.
Right. The rule states that responses from the server must explicitly declare whether they can be stored and reused by the client.
Right, let's expand on that. When the server sends a response back to the client, it includes specific HTTP headers, most notably the cache control header.
So the server is dictating the terms of memory.
Exactly. It might say, this data is highly volatile, do not cache this ever. Or it might say, this data is static, feel free to store it locally for 3,600 seconds.
Okay, but let me challenge this for a second.
Go for it.
Let's say I open a news app, and the server says, cache this list of headlines for an hour.
Okay.
I close the app.
Yeah.
10 minutes later, major breaking news happens.
Yeah.
I open the app again. If my phone is just reading from its local cache, isn't it going to show me outdated, stale headlines?
Yeah, that's a valid concern.
So isn't caching inherently risky?
Oh, absolutely. That is the exact tension engineers deal with every single day, the trade-off between speed and freshness. In fact, cache invalidation is famously one of the hardest problems in computer science. But REST requires the server to provide the mechanisms to handle this.
How so?
Well, The server might include something called an E tag in the header.
An E tag? What's that?
It's essentially a unique fingerprint for that specific version of the data.
Oh,
So when you reopen your news app 10 minutes later, the app doesn't just blindly show the old cache.
what does it do?
It sends a tiny lightning-fast request to the server saying, I have the headlines with fingerprint XYZ, has anything changed?
Ah, and if the breaking news hasn't happened yet?
The server responds with a tiny 304 not modified status.
Wait, so it sends 0 data?
Exactly 0 data. It essentially says your cache is still perfectly fresh, go ahead and use it.
Oh, wow. So it verifies the cache without having to re-download the entire payload.
That's the exact mechanism at play, and when you extrapolate that across millions of users, the developer benefit is just staggering.
I can imagine.
It results in massively reduced load on the database.
Right, because if your application requests a list of all the countries in the world for a drop-down menu, that list isn't changing.
Exactly. The server tells millions of smartphones to cache it for a month.
And the database is spared millions of redundant queries, saving immense compute power and bandwidth while providing the user with an instantaneous experience.
You've got it. It's incredibly efficient.
I'm starting to see how these rules build on each other to create that efficiency.
Yeah, they really do.
So the third principle is uniform interface, and the document calls this the defining characteristic of REST.
This rule is what prevents the Wild West scenario we discussed earlier.
The chaos of a million different menus.
Exactly. A uniform interface mandates a standardized way of communicating, regardless of the specific client or the specific server.
Okay, so it forces developers to use standard HTTP methods and standard URI structures, the web addresses, in a highly predictable way.
Right.
But if I were a developer ignoring this rule, what would my chaotic API look like?
Well, without a uniform interface, one developer on your team might create an endpoint to fetch user data and call the URL getUserData.
Okay.
Another developer working on the billing system might create an endpoint called fetchInvoiceInfo.
Oh, I see where this is going.
And a third developer might use userProfilerRetrieve.
That's a mess.
It is. Every single time a front-end developer wants to connect a new screen to the back-end, they have to read pages of documentation just to figure out what random verbs and nouns the back-end engineer decided to use that day.
It sounds like trying to navigate a city where every single neighborhood has invented its own unique shape and color for a stop sign.
That is a perfect way to visualize it.
Wow.
So by enforcing a uniform interface, we standardize the road signs. We use the HTTP verbs that get t, post, per t, deli against the actions. And the URL simply represents the noun, the resource.
So it's always get users, post invoices, delete comments.
Exactly. Once you learn the architectural grammar, you can guess how to interact with almost any part of an API system without even reading the manual.
It creates a predictable, logical ecosystem.
It really does.
That grammar is going to be crucial when we look at the actual code later. But let's keep moving. The fourth principle is layered system.
Right. So a layered system dictates that the architecture is composed of hierarchical layers. And this is the critical part. Each component cannot see beyond the immediate layer it is directly interacting with.
Okay, so when my mobile app sends an HTTP request, it thinks it is talking directly to the main database server.
Exactly. But in reality, it's almost certainly talking to a proxy server, which then talks to a load balancer, which then routes the traffic to a security firewall, which finally hands the request to one of 50 different application servers.
And the client on my phone is completely oblivious to all these invisible middlemen.
Completely oblivious.
That's wild.
And the developer benefit here is profound flexibility and security. Because the client is blind to the layers, the engineering team can radically alter the physical infrastructure without breaking the app.
So they can insert a new DDoS protection layer or distribute their database traffic across data centers in 3 different countries, and the client's code doesn't have to change one single character.
Exactly. The app just keeps handing the order to the waiter, totally unaware that the waiter might be handing it to a runner, who hands it to a sous chef, who hands it to the grill master.
That is such a robust way to build a system.
It really is.
So the fifth principle is code on demand. Now, the source explicitly marks this one as optional.
Yeah, it's the only one.
Why is this the only rule that isn't strictly enforced?
Well, code on demand simply means that a server can temporarily extend the functionality of a client by transferring actual executable code rather than just raw data.
What's a common example of that?
The most common example is a server sending a complex JavaScript file to a web browser.
Okay.
Suddenly, the browser can perform a sophisticated data visualization or run a specific cryptographic check locally on your machine.
So it allows the server to upgrade the client dynamically.
Right. However, it is optional because downloading and executing foreign code inherently introduces massive security risks and complexity.
Oh yeah, that makes sense. You're just running random code.
Exactly. An API can be perfectly RESTful without ever sending a single line of executable code.
Which brings us to the final principle, number 6, and this is a big one. Statelessness.
Yes.
The document states, no session data stored on server. Requests are self-contained. So the server retains absolutely zero memory of my previous interactions.
That's correct.
Now, if I stick with the restaurant analogy, this sounds terrible.
I know, it does.
I mean, this is a waiter with severe amnesia. I order an appetizer, they bring it. 10 minutes later, I flag him down and say, I'll have the steak now, and the waiter looks at me blankly and says, who are you? What table is this? Are you even a customer here?
Yeah, having to re-explain your entire existence for every single course sounds incredibly inefficient.
It sounds maddening. Why is this a rule?
It is definitely the most counterintuitive principle for anyone just getting into network architecture. It feels like a massive step backward in efficiency.
Right.
And you are right. If you only have one single waiter and one single table in your entire restaurant, amnesia is a terrible system.
The waiter spends half their time re-verifying who you are.
Exactly. But to understand why statelessness is the secret engine of the modern internet, you have to imagine a restaurant that spans the entire globe, with tens of millions of concurrent customers and 50,000 interchangeable waiters working at the exact same time.
Okay, a globally scaled restaurant. If the waiters did have memory in that scenario, what breaks?
Okay, so if the server stored a session state, meaning it dedicated a piece of its internal memory to remembering that you were sitting at table 12 and you already ordered the soup, then the specific waiter who took that first order is the only one who holds the context of your meal.
Oh.
So when you want to order your steak, you cannot talk to any of the other 49,999 waiters.
Because they have no idea who I am.
Right. You have to wait for that exact specific waiter to become available again.
And if that specific server gets overwhelmed with traffic, I experience severe lag.
Exactly. And worst of all, if that specific server crashes, if the waiter trips and drops their tray, your entire session is wiped out.
Wow.
You are violently disconnected from the application because your state was tied to a single fragile machine.
Okay, so by giving the waiter a memory, you essentially create a massive, brittle dependency.
Precisely. Statelessness eliminates that dependency entirely. It mandates that every single HTTP request you send must contain all the context necessary for any server to understand and fulfill it in total isolation.
So I don't just send a message saying, I'll have the steak.
No, you send a self-contained packet that says, I am customer ID 456 sitting at table 12. I have already been verified by security using this cryptographic token, and I am requesting this steak.
Because the request carries its own context, any available waiter can grab it.
Yes.
And how does that translate to the physical server racks running a major app?
It unlocks infinite horizontal scalability.
Right.
If a viral video sends a massive spike of traffic to your app, you don't need to try and upgrade one single massive supercomputer to hold millions of complex user sessions in its memory.
You just spin up 1,000 cheap, identical amnesiac servers.
Exactly, because no single server needs to remember any user. The load balancer can route your incoming request to any server that happens to have free CPU cycles at that exact millisecond.
And if a server physically catches fire and dies mid-request, it barely matters.
Nope. The client just resends the self-contained request, and a different server instantly picks it up.
That is wild.
That architectural amnesia is literally the only reason tech giants can serve billions of users simultaneously without the system grinding to a halt.
That is a total paradigm shift.
Yep.
The amnesia isn't a bug. It is the foundational feature that makes the workers completely interchangeable.
Yep, it's brilliant.
So we have the theoretical rules, we understand the physics, but how do we actually write the grammar?
What do you mean?
Like, if I am a client, how do I physically format a request to follow these rules?
Oh, gotcha. Well, to understand the grammar, we have to dissect the anatomy of a RESTful endpoint.
And the blueprint gives us a highly specific, practical example to tear apart.
It does. Imagine a developer looking at this string. Get https.api.dexipay.com v1 users1.rule admin.
To a layperson, that is just a messy web link.
Right, but to an architect, it's a perfectly structured, unambiguous sentence.
Let's break that sentence down into its components,
Yeah.
starting with the very first word. get T.
That is the HTTP method. It is the verb of our sentence.
So it explicitly tells the server what type of action we intend to perform.
Exactly. In REST, these verbs map directly to a concept called CR-root operations.
CRE. Create, read, update, and delete.
Yep, the 4 basic functions of persistent storage.
So get is strictly for reading data.
Right. You're asking the server to return information, and you are promising not to alter the database in any way.
And post.
Post is for creating a brand new record, like submitting a registration form.
What about POD or PASEH?
Those are for updating an existing record.
And delete is obviously self-explanatory.
Exactly. So by leading with getET, we are firmly stating, I only want to read some information.
Okay. The next chunk is the base URL, https://api.dexipay.com. Now, I know this is the domain, like the address of the building, but physically, how does my phone know where dexipay.com actually is? It's not a real physical location.
This is where we touch on the underlying plumbing of the internet.
Okay, let's hear it.
Computers do not understand words like DexiPay. They only understand IP addresses, which are strings of numbers like 192.168.1.1.
Right.
So when your phone tries to send this request, it first does a DNS lookup.
The domain name system.
Yes, which is essentially the phone book of the internet. Your phone pings a DNS server and asks, what is the numeric IP address for api.dexipay.com?
And the DNS server replies with the specific numerical coordinates of the server farm hosting that API.
Exactly. Your request is then routed across the physical infrastructure of the internet to hit that exact machine.
So the base URL gets us to the correct front door of the factory. Then we have the path. V1 users 1.
This is the uniform interface principle in physical action.
Oh, right.
The path identifies the specific noun, the exact resource within the factory that we want to interact with. Notice the logic of the hierarchy.
V1 tells the server we are communicating using version 1 of the API rules.
Which is crucial because if the company ever releases a massive code-breaking version 2 upgrade, older mobile apps that haven't been updated will still securely route to V1 and continue functioning.
That makes total sense. Next, users defines the collection of resources we are targeting.
Right. And the one at the end is the unique identifier.
Because we don't want a massive list of every user, we want the specific data for the user whose database ID is 1.
Exactly.
We read from DexiPay using version 1 rules, the user whose ID is 1. It really is just a sentence.
It's beautifully simple.
And finally, tacked on at the very end, separated by a question mark, we have role admin, the query parameters.
Query parameters are the optional modifiers. They are the adjectives and adverbs of our sentence.
So they do not change the core resource we are targeting, but they modify how we want the server to filter or format the response.
In this case, we might be saying fetch user 1, but only return the data if they possess an admin role.
Oh, I see.
Query parameters are heavily used for things like search filters or paginating data, so you only receive 20 results at a time instead of a million.
Okay, the grammar makes perfect sense, but I want to pivot from the theoretical to the intensely practical.
Sure.
If I am a junior developer and it's Tuesday morning and I am tasked with building this system, what am I physically looking at?
Right, you just have a blank screen.
Exactly. I have a blank laptop screen. How do I construct these invisible waiters? The document outlines a local API development tech stack consisting of 4 core tools. Walk me through the actual workflow of setting this up.
Okay, so this is the bridge between academia and engineering. A developer does not write code directly on the live internet.
Obviously not.
They build a sandbox, a miniature replica of the internet on their local laptop. To do that, they need to install these 4 specific tools. The first is a local web server environment. The blueprint highlights a tool called Uniform Server.
Now, why do I need to download a server? Doesn't my Mac or Windows machine already have the ability to connect to the internet?
Your laptop is configured to be a brilliant client. It is great at sending requests to the outside world,
Okay.
but it is not configured to sit there and listen for incoming HTTP traffic, nor does it have an enterprise-grade relational database running in the background.
Oh, right. You have to turn your laptop into the kitchen.
Exactly. Uniform Server is a software package that instantly installs Apache, a web server daemon that listens for HTTP requests, and MySQL, the database engine.
Okay, but why does the blueprint specifically recommend Uniform Server?
Because it is zero install and lightweight. It doesn't bury configuration files deep inside your operating system's registry. It runs entirely inside a single folder on your desktop.
So I avoid port conflicts, like when Skype and Apache both try to use port 80 and crash my machine.
Yes, and you keep your local laptop totally pristine.
So I have my miniature isolated test kitchen running on my desktop. The web server is listening, the database is spinning. Now I need to actually install the Laravel framework to write the code. Tool number 2 is Composer.
Right. Because when you build a modern application, you are not writing every single mathematical function and security protocol from absolute scratch.
That would take a lifetime.
It really would. You rely on an ecosystem of pre-written, highly tested, open source libraries. You might need a library that generates barcodes, a library that integrates with Stripe for credit card processing, and of course, the massive code base of the Laravel framework itself.
And Composer manages all of that.
It is the supply chain manager for PHP. It's a command line tool. You type a single command like Composer create project Laravel, and Composer connects to the internet, figures out the complex web of dependencies.
Meaning, which library requires which other library to function.
Exactly. It downloads hundreds of packages, ensures all the version numbers are compatible, and meticulously organizes them into your project folder. It totally eliminates dependency hell.
That's a lifesaver. So Composer brings all the advanced machinery into my local kitchen. Now I need to actually write the recipes. Tool number 3 is VS Code.
Visual Studio Code is the IDE, the Integrated Development Environment. This is the application where the developer spends 90% of their day.
It's an incredibly powerful text editor that highlights syntax errors and autocompletes code.
But its real power, especially for Laravel development, is the deeply integrated terminal.
Okay.
Laravel is a highly command-driven framework. Developers use an internal tool called Artisan.
Artisan.
Yeah, so instead of manually creating a complex file with 50 lines of boilerplate code, the developer opens the VS Code terminal and types PHP artisanmake.controller user controller.
And the framework instantly generates a perfectly structured file in the exact correct directory.
Exactly. VS Code is the command center where you write the logic and orchestrate the framework simultaneously.
So I've written some code. I've built a POSD endpoint that is supposed to accept a user's registration data and save it to the database. But I'm a back-end developer. The front-end team hasn't built the iOS app or the website yet. How do I test if my endpoint actually works? I don't have a physical submit button to click.
That is the exact problem solved by the fourth tool in the stack, Echo API.
Echo API.
Echo API is a specialized offline desktop application designed purely for API debugging and simulation.
Okay.
It allows you to manually construct the raw HTTP request that a mobile app would send. You open Echo API, you select PostHis from a dropdown, you type in your local test URL, you manually build a JSON payload containing a fake email and password, and you hit send.
And Echo API fires that request at my local uniform server.
Yep, it catches the response and displays the raw JSON output on your screen. You can see the exact HTTP status code, the headers, and the data.
It is the wind tunnel where you test the aerodynamics of your API before anyone else ever uses it.
I love that analogy, yes.
And as a byproduct, doesn't it help solve the documentation problem? Because eventually I have to explain to the iOS team exactly how to talk to the system I just built.
Absolutely. The moment your API is stable, you have to publish the menu.
Right.
If the mobile developers don't know the exact spelling of the JSON payload you expect, the integration fails. Echo API can take all those test requests you built and automatically generate beautiful interactive documentation.
It creates a standardized contract between the back-end and front-end teams.
Exactly.
So we have the theory, we understand the grammar, and we have our local workbench fully set up. Now we can trace the actual anatomy of a request in motion.
Let's do it.
When I finally tap that submit button on my phone, what is the microscopic chain of events that happens inside the Laravel framework? The blueprint outlines an 8-step journey. Let's walk through the physical flow of data, step by step.
Okay, let's assume the client is sending a POST request to register a new account. The user hits submit. Step 1 is the client origin.
The mobile app encrypts the payload, packages the email, password, and name into the HTTP protocol, and fires it over the network.
Exactly. It arrives at the server and enters the Laravel application.
It enters the application and immediately hits step 2, the route. The document calls this the API.php switchboard.
The routing file is the grand central station of the framework. It receives this raw incoming traffic. It inspects the HTTP verb, POST, and the URI path users.
Okay.
It consults its internal registry and says, a PST request targeting the user's endpoint. I know exactly which part of the application is responsible for this.
It physically routes the execution flow of the code down a specific hallway toward a specific controller.
Right. But the data doesn't get to the brain of the application yet. It is intercepted at step 3, middleware.
Middleware.
Middleware acts as a series of checkpoints or bouncers standing in that hallway. Before the application expends serious CPU cycles processing the logic, the middleware inspects the request.
What is it looking for?
It asks, is this request coming from an allowed IP address? Is the payload suspiciously large, indicating a potential buffer overflow attack? Are they trying to hit the endpoint too many times a second?
And if the request fails any of these checks?
The middleware terminates the journey instantly and returns an error response. The core application logic is completely shielded.
Okay, assuming it survives the gauntlet of bouncers, it arrives at step 4, the controller, the brain of the operation.
Yes. The routing switchboard directed the traffic to a specific method inside the user controller. The controller is a PHP class that holds the business logic.
Okay.
It receives the incoming data and says, my objective is to create a new user record. To accomplish this, I need to communicate with the database.
But here's the friction. The controller is written in PHP, an object-oriented programming language. The database, MySQL, does not understand PHP,
No, it doesn't. It only understands raw SQL queries.
which necessitates step 5, the model,
Mm-hmm.
and specifically Laravel's Eloquent ORM.
ORM stands for Object Relational Mapper. This is arguably the most powerful subsystem in the entire framework.
How does it work?
A model is a simple PHP class that acts as an ambassador to a specific database table. So instead of the controller trying to formulate a complex string of raw database syntax, the controller simply talks to the model in native PHP.
It essentially says, hey, user model, take this array of data, create a new object, and execute the save command.
Exactly. And the ORM handles the translation invisibly.
Wow.
Eloquent dynamically translates that simple PHP object manipulation into the exact complex SQL query required by whichever database engine you happen to be running and fires it down the wire.
That hits step 6, the database.
The SQL query arrives at MySQL. The database engine executes the right operation, physically magnetizing the sectors on the hard drive or flashing the solid-state memory, permanently storing the new user row.
And the database then sends a confirmation signal back up to the model,
Yeah.
usually including the newly generated unique ID for that user.
Right. So the core job is done, but we can't just leave the client hanging. We need to send the data back.
Which brings us to step 7, the API resource, the formatter.
Because the raw object coming back from the database is messy. It contains the data we want, but it also contains internal database timestamps. And crucially, it might contain the hashed version of the user's password.
Right, and if we just blindly return that raw object to the client, we are leaking sensitive architectural data.
Exactly. The API resource acts as a strict formatting filter. It receives the raw database object and maps it into a precise, perfectly structured JSON array, ensuring that only the safe, requested data is exposed to the outside world.
And finally, step 8, the response.
The framework takes that clean JSON payload, attaches the correct HTTP status code, in this case, a 201 created to indicate successful resource generation, compiles it back into an HTTP response packet, and fires it out of the server across the network back to the mobile app.
The app receives the 201 code, updates the UI to show a green checkmark, and the microscopic journey is complete.
Exactly. It's a journey, but it happens in milliseconds.
That flow is incredibly logical. Root to middleware to controller to model to DB and back out.
Yeah.
But I want to circle back to step 2, the routing file. Because earlier we talked about the uniform interface and how REST mandates standardizing the CRU'd operations.
Right.
If every resource needs a way to create, read, update, and delete, that means a developer has to write at least 5 different routing rules for every single table in their database.
Yeah, you'd think so.
That sounds like a massive wall of repetitive code in the API.php file.
It would be if developers had to write them all manually. But the blueprint highlights a fascinating efficiency in Laravel called resource routing.
Okay, what is that?
Because the REST pattern is so mathematically universal, the framework provides a macroscopic shortcut. Instead of writing 5 separate lines of code to define the get, post, put t, and delete endpoints for a user, a developer writes one single line, route.apay resource users, usercontroller.class.
It's like hiring a general manager who instantly writes the exact, highly detailed job descriptions for 5 specialized employees, completely standardizing the workflow without you having to micromanage the details.
That one line of code acts as a master traffic cop. Under the hood, it automatically and invisibly generates 5 strictly REST-compliant routes.
Wow.
It maps a get T request for users directly to the index method to list everyone. It maps a post request to users directly to the store method to create a new one.
And it maps GetT users to the show method to read a single profile, and similarly wires up the update and delete pathways.
Exactly. The reduction in human error there is massive. You literally cannot misspell the URL or use the wrong HTTP verb for an update because the framework generates the blueprint based on theoretical best practices.
You just tell it the noun and it handles the verbs.
Exactly. It forces junior developers into an enterprise-grade architectural discipline while simultaneously saving senior developers hours of typing boilerplate code. It is the perfect marriage of strict theory and practical tooling.
Okay, that covers the routing layer brilliantly. But I want to dig much deeper into the actual data manipulation. Let's move into the data engine and the shields. We briefly touched on Eloquent ORM translating PHP into SQL.
Right.
But why is writing raw SQL considered such a bad practice in modern applications? What is the actual danger?
To understand the danger, you have to look at how brittle raw SQL syntax is. Imagine you are writing a complex query to pull a user's data and their recent orders. In raw SQL, you might write a string literal in your code that looks like: select from users inner join orders on users.id orders.userid, where users.email at attest@test.com.
It looks a bit like algebraic gibberish.
It is highly specific syntax. Now, imagine your database administrator decides that the column name email is too vague, and they change the physical database column to be named email address.
Oh, the string literal in my code is now looking for a column that doesn't exist.
Exactly. The query will catastrophically fail, throwing a fatal error and crashing that part of the application.
That's bad.
And the nightmare is that you might have written that raw SQL string in 50 different files across your entire code base.
Oh no.
You have to use a find and replace tool and pray you don't accidentally replace the word email somewhere it shouldn't be changed. Raw SQL tightly couples your application logic to the physical schema of the database.
And Eloquent ORM severs that coupling.
By interacting with PHP objects instead of strings of text, Eloquent abstracts the schema. If you use Eloquent, you just say user orders.
And the framework looks at its internal configuration, dynamically constructs the correct SQL query on the fly, and executes it safely.
Right. If a column name changes, you update the configuration in one single central place, and every single query in your entire application instantly adapts.
But that brings up a larger problem. You just mentioned the database administrator changing a column name. How does a team safely manage changes to the database structure once an app is live? In the old days, how did people add a new column to a table with 1 million users in it?
The old days were terrifying. A developer would literally log into the live production database server using a graphical interface, right-click on a table, select Add Column, type in the details, and hit Save.
And if they made a typo, or if they accidentally clicked Drop Table,
The data was gone. And even if they didn't make a mistake, there was no historical record of what they did.
right?
The other developers on the team would pull the latest code, try to run the application locally, and it would crash because their local database didn't have the new column that was manually added to production. It was synchronization nightmare.
The document says the solution to this is migrations, calling them version control for your database.
Migrations completely eliminate manual database intervention. Instead of clicking buttons in a UI, developers write specific PHP blueprints that describe the structural changes they want to make. They write a file that says, create a table called users, add a string column called email, make it unique, add a timestamp. Because this is just a text file containing PHP code, it is committed to the Git repository right alongside the application logic.
It creates an immutable historical ledger of every single change ever made to the database architecture since the day the project started.
Yes, the workflow transforms. When a new developer joins the team and downloads the codebase, their local database is totally empty. They go to the VS Code terminal and type one command at PHP artisan migrate.
And the framework finds all those historical blueprint files, executes them in chronological order, and within seconds constructs a mathematically perfect replica of the production database schema on their local machine.
Exactly. When it is time to deploy to the live server, you don't log in and click buttons. You run the automated migration command. It makes database evolution entirely predictable and safe.
Okay, so Eloquent gives us a safe way to interact with the data, and migrations give us a safe way to build the structure. But what about the data itself? We talked about the middleware bouncers earlier, but the blueprint specifically highlights a component called the validation shield. Why is this so crucial? If my mobile app already has code that prevents the user from typing letters into a phone number field, why do I need to re-verify it on the server?
Because you can never, under any circumstances, trust the client. That is the golden rule of backend security.
Never trust the client.
Never. Your mobile app might have a great user interface that politely stops someone from entering letters into a phone number field. But a malicious attacker doesn't use your mobile app.
What do they use?
They use a tool like Echo API. They bypass your front-end interface entirely, construct a raw HTTP POST request, and attempt to inject a massive SQL command into that phone number field to try and delete your database.
They just talk directly to the waiter and slip him a poisoned note.
Precisely. If that poison payload reaches the controller, or worse, reaches the Eloquent model, your system is compromised. The validation shield sits right in front of the controller, acting as a cryptographic quarantine zone.
Okay.
The developer defines a strict array of rules that the incoming payload must survive before it is allowed to proceed. The blueprint gives a very clear example of an array rule for an email address. Email required.melanique.users.
Walk me through the mechanics of that specific rule.
It is a gauntlet with 3 specific gates. The payload arrives. The shield checks the first gate, required. Does the payload even contain a field labeled email?
If it is blank or missing, the payload is rejected.
Right. If it passes, it hits the second gate, email. The framework runs a complex regular expression algorithm against the string to ensure it mathematically conforms to the international standard for an email address.
So it must contain an @ symbol, a domain name, and a top-level domain.
Exactly. If it's just random text, it is rejected.
And the final gate, unique.users.
This is the most powerful one. The shield briefly pauses, reaches out to the database, and executes a lightning-fast query against the users table to see if that exact email address already exists. It ensures data integrity before the controller ever gets involved.
What actually happens to the rejected data? If I try to register with a malformed email, how does the system respond? Does it crash?
It handles the failure with absolute grace. The auto-reject mechanism kicks in. The controller is never notified. The database is never touched.
Wow.
The framework intercepts the bad data, automatically constructs a beautifully formatted JSON error response, attaches a 422 unprocessable entity HTTP status code, and fires it back to the client.
The 422 code is the server's way of saying, your HTTP request was structurally sound, and I understood what you wanted to do, but the actual data payload you provided is semantic garbage. Fix it and try again.
Exactly. The client receives the JSON, reads the specific error message generated by the shield. The email must be a valid email address, and displays it to the user. Only perfectly clean, rigorously verified data is ever allowed to pass through the shield and interact with the application's brain.
It is an incredibly elegant defense perimeter. We have protected what data is entering the system. But we have to solve the problem of the amnesiac waiter.
Yeah.
We have to protect who is sending the data while maintaining the strict rule of statelessness. This brings us to the velvet rope: security and authorization. How do I stay logged in if the server is mathematically forbidden from remembering me?
The blueprint details the industry standard solution for this, enforcing stateless security via Laravel Sanctum. Sanctum is a specialized authentication package that embraces amnesia rather than fighting it. It relies on cryptographic token issuance.
Let's trace the life cycle of a login.
Step 1. The client sends a POST request to a login endpoint containing their username and password. The server checks the database, verifies the password hash, and confirms your identity. But instead of allocating a chunk of memory to remember that you are logged in, the server utilizes a cryptographic algorithm to generate a massive mathematically unique string of random characters.
This is the Sanctum token.
Yes. The server hands this token back to the client in a JSON response.
It's like the bouncer checking my ID at the door, verifying I am over 21, and then clamping a VIP wristband onto my arm.
Exactly the mechanism. And the moment it hands you that wristband, the server instantly enforces its amnesia. It drops all memory of the interaction. It is ready for the next completely unrelated request.
So how does the wristband work when I want to access my private data 5 minutes later?
Your mobile app securely stores that token in its local keychain. For every single subsequent request your app makes to the API, whether it's fetching your profile or posting a comment, the app automatically injects that token into a specific HTTP header.
It looks like this: authorization, bearer token string. You are literally bearing the token to the server with every interaction.
No.
And how does the server know I didn't just type out a random string of characters and forge the wristband? If it doesn't remember me, how can it verify the token?
Because of the cryptographic signature. When the server generated the token originally, it didn't just spit out random letters. It took your user ID, combined it with a secret, highly complex app key that only the server knows, and mathematically hashed them together to create a signature.
Okay, I follow.
So when you hand the token back, the Sanctum middleware intercepts it. It splits the token apart, looks at the user ID, and runs the mathematical hashing algorithm again using its secret key.
If the resulting math matches the signature on the token, the server knows with absolute cryptographic certainty that it was the entity that issued that token and that it has not been tampered with.
You've got it. It mathematically verifies the passport without needing to look you up in a centralized registry. That is staggering.
You get all the security of a logged-in session without sacrificing the infinite horizontal scalability of a stateless architecture. Any server in a massive global cluster can mathematically verify that token independently.
It is the only way to scale authentication to millions of users.
But having a valid wristband only solves half the problem. Authentication proves who I am. But just because I am a registered user with a valid token does not mean I have the authority to do anything.
Right.
I should absolutely be allowed to edit my own profile. But I shouldn't be allowed to edit your profile. We both have valid wristbands, but our permissions are different. How does the API enforce granular control?
You are distinguishing between authentication and authorization. It is a critical line in security architecture. Authentication answers, who is this? Authorization answers, are they allowed to perform this specific action on this specific asset?
Okay, so to handle authorization, Laravel employs two distinct layers of control, gates and policies.
Yes. The blueprint outlines a flowchart. First, the token passes the authentication check. Then it hits a policy node.
Explain what a policy is physically doing.
Imagine your request is to update the title of a specific blog post. The routing sends the request to the controller. But before the controller executes the Eloquent command to save the new title, it halts and consults the post policy.
So a policy is a dedicated PHP class explicitly designed to house the security logic for one specific database model.
Exactly. The controller essentially asks the policy, can the user holding this token update post ID 50?
What logic is inside the policy?
The policy executes a quick comparison. It looks at the user ID embedded in the token. Then it queries the database for post ID 50 and looks at the authority column.
Oh, I see.
It compares the two integers. If they match, the policy returns a Boolean true. The controller receives the green light, saves the data, and returns a 200 OK.
And if I am a malicious user trying to edit a post I didn't write?
The integers do not match. The policy immediately returns false. The framework intercepts this rejection and violently halts the request. It throws a 403 forbidden exception back to the client.
This is a very different response than a 401. A 401 unauthorized means your token was missing or mathematically invalid. The bouncer didn't recognize you.
Exactly.
A 403 forbidden means the system knows exactly who you are, but you are absolutely not permitted to access the VIP room you're just trying to enter.
That's a great analogy.
That handles specific resources beautifully. But the document also mentions gates. What is the difference between a gate and a policy?
The difference is entirely about scope and complexity. Policies are robust classes tied to specific models, evaluating complex relationships like ownership. Gates are much simpler, closure-based checks.
A closure is just an anonymous, self-contained PHP function.
Right. Gates are typically defined centrally when the application first boots up, and they are used for sweeping global permissions that don't depend on a specific database row.
Give me an example.
For example, you might define a gate called Access Admin Dashboard. It simply checks if the user's role is set to administrator. It doesn't matter what specific resource they are trying to touch. If that simple function returns false, they are locked out of the entire admin section.
So gates are the broad general bouncers at the front door of the club. And policies are the highly trained security guards standing outside individual VIP booths checking specific guest lists.
Yes.
By abstracting all of this logic into dedicated files, the actual controller remains incredibly clean. It doesn't get bloated with messy Eiffel statements checking user roles. It just asks the framework, is this allowed? And trusts the blueprint.
Exactly. It enforces the separation of concerns.
We have engineered a fortress. The API routes perfectly. It interacts with the database safely. It is shielded against malicious payloads. And it is secured with cryptographic tokens and granular access policies. We have built an enterprise-grade system.
But there's one final massive hurdle: performance.
Right. We talked earlier about REST's promise of a lightning-fast user experience. But let's look at reality.
Reality is heavy.
Exactly. Let's imagine I register for a new financial application. I hit submit. On the back end, the server has to do a lot more than just save my name to the database. It needs to reach out to a third-party API like Stripe to create a complex billing profile.
Yep.
It needs to generate a customized, multi-page PDF welcome packet. And it needs to connect to an external SMTP server to send me a welcome email. If the API forces my mobile app to sit and wait while it performs all of those heavy sequential tasks on the main thread, the app is going to feel broken.
Oh, completely broken.
The screen will freeze with a loading spinner for 5, maybe 10 seconds. The user will assume it crashed, force quit the app, and leave a 1-star review.
That is the nightmare scenario for synchronous processing. If you execute long-running tasks on the main API thread, you are tying up the waiter.
Back to the restaurant.
Yes, if the waiter is standing in the kitchen waiting 10 minutes for a complex dish to cook, they cannot take orders from any other tables. The entire restaurant grinds to a halt. To maintain lightning-fast performance, we must implement background workers.
The visual in the blueprint for this is incredibly helpful. It shows the main API thread as a straight, fast, uninterrupted red line. And dropping down from that line is a pipe leading to a background queue belt. Explain how this offloading process physically works.
Well, the fundamental goal of an API is to return an HTTP response to the client as fast as physics will allow. So when the heavy registration request hits the controller does the fast part first. It saves the user to the database in a few milliseconds.
Okay.
But instead of halting to generate the PDF and send the email, it packages those instructions into isolated objects called jobs. It creates a generate welcome PDF job and a send welcome email job.
It basically writes the instructions on a clipboard and drops the clipboard into a basket.
Perfect analogy. It drops the jobs onto the background queue belt, which is often powered by an ultra-fast memory store like Redis. The absolute millisecond it drops those jobs onto the belt, the main API thread considers its work done.
Wow, really?
Yes. It is completely freed up. It instantly fires a 201 created JSON response back to the client. From the user's perspective, the registration was instantaneous. The app immediately transitions to the home screen.
But the heavy lifting still has to be done. Who is reading the clipboards?
Running silently in the background of your server environment, completely separate from the web traffic listening for HTTP requests, are worker daemons.
Worker daemons.
These are persistent PHP processes that just sit at the end of the queue belt, infinitely looping, waiting for a job to appear.
So the moment a job drops, a worker process grabs the send welcome email job and begins executing the heavy code.
Exactly. It talks to the SMTP server. If the mail server takes 5 seconds to respond, it doesn't matter. The worker is blocked, but the primary API thread is completely unaffected. It is still taking new HTTP requests at lightning speed.
That is brilliant. You delegate all the time-consuming chores to a dedicated crew in the back room so the front-of-house staff can focus entirely on immediate customer service. But the blueprint introduces another architectural concept right alongside queues, which is decoupling via events and listeners. This seems to solve a different problem than just speed.
Events and listeners solve the problem of code entanglement. Let's go back to our synchronous controller for a moment. If the user controller has to explicitly command the system to send an email, and command the system to generate a PDF, and command the system to talk to Stripe, that controller becomes a massive, bloated file.
Right, it has to import the mailer library, the PDF library, and the billing SDK.
Exactly. It violates the principle of separation of concerns. The controller should only care about HTTP traffic, not how to format a PDF.
If the controller's doing all of that, it becomes the single point of failure for the entire application. How does the observer pattern untangle this?
It replaces direct commands with broad announcements. Instead of the controller dictating specific actions, it simply announces a fact to the entire framework. It fires an event.
Okay, the blueprint shows a central red circle labeled event, user registered.
Right, so the controller saves the data to the database, shouts, "A user just registered," into the application ether, and immediately finishes its cycle. It literally does not care if anyone is listening or what they do with the information.
And who is listening on the other side?
The listeners. The blueprint shows 3 separate autonomous classes tethered to that event. Send welcome email, create Stripe profile, and logati activity.
Okay.
These are independent files that sit in the background listening for that specific broadcast. The moment they hear user registered, they wake up, grab the user payload attached to the event, and execute their specific logic, often pushing themselves onto the background queue we just discussed.
So the email listener knows exactly how to format the email, and the Stripe listener knows exactly how to talk to the billing API. The logic is completely isolated.
Exactly.
Think about how powerful this is for a team. If the marketing department decides 6 months from now that every new user also needs to be subscribed to a MailChimp newsletter, the engineering team does not have to touch the user controller at all.
Nope. They don't risk breaking the core registration flow. They just create one new file subscribe to newsletter listener and tell it to listen for the user registered event. That is the ultimate definition of modularity. Your codebase becomes a collection of highly specialized, independent systems that react autonomously to changes in state.
It's like a finely tuned orchestra, where every musician knows their cues, playing their part perfectly without the conductor having to walk over and tap them on the shoulder every few seconds.
By decoupling logic via events and offloading heavy execution via queues, developers transform a simple web script into an enterprise-grade, highly resilient data engine.
We have covered an immense amount of ground. We've been deep in the engine room, inspecting the individual gears and pistons, the routing switchboards, the ORM translation streams, the cryptographic tokens, the background daemons. But to truly synthesize this, we need to zoom all the way back out.
Let's do it.
We need to look at the entire factory floor from above. The final section of our source document, the master blueprint, explicitly maps the abstract academic theories of REST that we discussed at the very beginning directly onto the physical Laravel tooling we just explored. Let's walk through the synthesis.
This is where it all clicks together. It proves that a framework like Laravel isn't just an arbitrary collection of helper functions. It is a deliberate, physical manifestation of Roy Fielding's architectural theory. Let's match the theoretical rules to the practical tools. The source maps resources directly to Eloquent ORM.
REST dictates that an API must be a collection of distinct identifiable nouns, users, orders, comments. Eloquent ORM provides the physical structure to make this a reality. Each model file represents a specific resource, providing a standardized, object-oriented way to interact with the underlying database rows.
Exactly. Next, the theory of statelessness is mapped directly to Sanctum middleware. REST demands that every single request is self-contained and the server suffers from amnesia to ensure infinite scalability.
Right, and Sanctum enforces this architectural law by demanding a mathematically verifiable cryptographic token in the header of every single request, allowing for secure identification without ever relying on stateful server memory.
Yes. The layered system principle maps to Laravel's middleware stack. REST requires that the client is oblivious to invisible proxies and security checkpoints.
Laravel's middleware, which handles the validation shields, the rate limiters that prevent spam, and course headers that manage browser security policies, acts as these exact physical layers. They intercept, inspect, and modify the HTTP request invisibly before it is ever allowed to reach the core application logic.
And finally, the uniform interface principle maps directly to API resource controllers. Russia demands standardized, predictable communication across the entire ecosystem.
The root.api resource shortcut that acts as the traffic cop, combined with the API resource JSON formatters that filter the output, enforces absolute uniformity. It guarantees that every single resource in your application speaks the exact same CRU grammar and returns identically structured JSON payloads.
It is incredibly satisfying to see abstract computer science theory align so perfectly with practical engineering tools. Let's trace the complete life cycle of a request one last time, putting all the pieces of the blueprint together. Picture the factory in motion.
The HTTP request arrives from the client across the internet. It enters the factory through the routing switchboard, hitting api.php. The traffic cop immediately knows which department to send it to.
But before it can proceed down the hallway, it hits the gates. It hits the Sanctum and validation middleware. The bouncer cryptographically verifies the signature on the token to ensure authentication.
Then, the validation shield inspects the JSON payload against strict arrays of rules, rejecting any malformed or malicious data with a 422 error. Only pure, verified requests survive the gauntlet.
The surviving request moves into the center of the factory, reaching the controller. The controller executes the core logic, but first it consults a policy node to verify granular authorization, ensuring the user actually owns the data they're trying to manipulate.
Once approved, the controller needs to talk to the basement. It utilizes the Eloquent ORM, bypassing brittle raw SQL, to seamlessly translate PHP object commands into dynamic queries, interacting safely with the relational database to permanently write the data to disk.
And if there's heavy lifting required, like processing a credit card or formatting a PDF,
The controller fires an event into the ether, and listeners instantly drop instruction clipboards onto the background queue belt. Worker daemons silently pick them up and process them off the main thread, ensuring the API never blocks incoming traffic.
With the database updated, we prep the response for shipping. The raw, messy database object is passed through an API resource formatter. It strips out sensitive internals like password hashes and shapes the data into a beautiful, standardized JSON structure.
And finally, out the door. The clean JSON response, complete with a 200 OK or 201 created HTTP status code, is packaged up and fired back across the fiber optic cables to the client. The screen updates. The cycle is complete. Lightning fast, mathematically secure, and infinitely scalable.
By mapping rigid REST theory directly to modular tools, developers transform abstract architecture into physical, maintainable digital infrastructure. That is the ultimate takeaway of this document. It is the difference between simply knowing how an internal combustion engine works in theory and actually holding the wrench to build one.
It gives you an entirely new lens through which to view the digital world.
It really does.
We have reached the end of this incredibly dense deep dive. I want to thank you, the listener, for sticking with us through the technical weeds. We started with a simple analogy of a waiter in a restaurant. We descended all the way down into the microscopic code of routing files and database mappers, and we came back up to see the complete, fully realized architectural machine in motion.
You are no longer just a casual user blindly tapping a piece of glass.
You now hold the literal blueprints to how the modern internet is constructed. You understand the invisible physical and theoretical rules that govern global data flow. Every time an app loads instantly on your phone, you now know about the hidden background queues, the cryptographic signatures, and the cache headers, making it physically possible.
You understand the mechanics behind the magic.
But before we wrap up, I want to leave you with a final thought. Something to chew on that builds on everything we just discussed. We have spent this entire time marveling at how developers use these specific tools to manually build endpoints. We looked at how root.api resource allows a human engineer to write one single line of code, and the framework automatically, predictably generates 5 perfectly standardized endpoints based on strict REST theory. We essentially celebrated the peak of current framework efficiency for humans.
It is a highly optimized system.
Right, but here is the provocative question. If we have reached a point where the abstract architectural rules of the internet map so perfectly, so predictably, and so rigidly to these modular tools, what is the logical next step? We are currently watching artificial intelligence coding models advance at an absolutely staggering rate. These AI models understand Roy Fielding's REST principles perfectly. They have ingested the entire internet so they understand Laravel syntax flawlessly. If building a CRO endpoint, generating a migration file, and applying a validation shield is this standardized and rule-based, how long until human developers stop writing the actual endpoints entirely?
That is a deeply disruptive implication for the industry.
Are we rapidly entering an era where human software engineers transition entirely from being coders who painstakingly write the PHP syntax to being pure architects, where you simply sit at your computer and tell an AI agent, I need a scalable REST resource for handling hospital patient records, ensure strict HIPAA data compliance and granular policy authorization, and the machines instantly flawlessly generate the migrations, the Eloquent models, the validation shields, the complex policies, and wire up the background queues. When you tap your smartphone screen in 5 years, will the invisible, globally distributed chain reaction you trigger have been entirely built by an artificial intelligence that merely consulted the exact same blueprints we studied today? Something to think about the next time you place a digital order with your API waiter. Until next time.